Are there any questions?
For master set, I got questions, for number 7, 8, 10, 11.
7, 8, 10, 11?
Yeah.
So, wait, make sure I'm in the right one. Oh, wrong class. Not that. I don't have that one in front of me right now. Here. Oh, thank you. All right, so 7, consider a standing wave. That's the third harmonic. Is that? All right. Draw the wave and write the number of antinodes in the wave. If it is in a medium with 2 fixed ends, 1 fixed, 1 free, and then 2 free ends. So when dealing with one of those problems, remember that fixed. And before I get too frustrated with the markers, let's just take these and put them off to the side. A fixed end will show up as a node, and a free end will show up as an antinode. So if I have 2 fixed, that means I've got 2 nodes at the ends. And so that's the simplest for 2 fixed ends. So that's the first harmonic. Every time you go to the next harmonic, you're going to add half a wave. So if that's the first harmonic, the second harmonic, that's half a wave, here's a full wave, and then the third harmonic, if you recall, a full wave basically has, that would be a full wave right there, or that is also a full wave. So basically, you're starting at some point, you go until you get back to the same point and repeat it. So for something that's repeated. So if I'm doing this, if I start here, that wave will end when I'm basically at the same position and the same slope. So that's one wavelength. Now, when you're dealing with the harmonics, that means you're starting at either an antinode or a node. So I'm starting here and going till I get to the next peak, or I'm starting here and going till I get to the next trough, or starting in the middle and go till I get to the next middle when it's sloped upwards. So that's all that I'm doing here. So half a wave, full wave, 1.5 waves. It's very similar to the 2 free ends because we'll just have antinodes instead of nodes. And the way it's typically drawn, like that. So 2 free ends, you have that, and then you just add a half wave each time. Just making sure so this is 2 free. The trick is for the 1 fixed, 1 free end, the simplest wave looks like that. You're gonna add a half a wave to get to the third harmonic. There's no second harmonic for one fixed, one free. And that's the one trick. So you're just, so when I go from the first harmonic to the third, I'll go from the first harmonic to the third harmonic, adding a half a wave. And then we'll just take the two fixed for the number of nodes or antinodes. In this particular question, it asks, draw the wave, write the number of antinodes. Well, antinode, 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 so I have 3 antinodes. This is just the first harmonic here, but that's 2 antinodes. So, yeah, Chris?
So we're only counting the antinodes on one side, not on both sides.
Oh, it counts as an that both of them together count as an
Oh,
antinode.
okay.
And again, it's representing that point when it's vibrating a whole lot that it looks like that are in both places at once.
What question were you guys just on?
This was question number 7. Any other questions on number 7? Yes.
The 2 free ends, is that the same, just like you said, whenever it's a full wave, the antinode it counts for that whole space, is that the same as on the free ends as well?
Yeah, so this would be, this has 2 antinodes,
Okay.
here and here.
Okay.
Other questions on number 7 from the master set? Try to get out of the way. Please sidestep instead.
Thank you.
There's a board back there. Sometimes wonder if someone's going to do a compilation of my klutziest moments. But considering there's over 1,600 videos, probably closer to 1,700 at this point, no one's going to put themselves through that kind of agony. All right, number 8. I think that was one of the other ones.
Yeah.
End of 60 hertz string vibrator, which the string is tied, is 1.2 meters from the pulley. At the end of the string, which is hanging from the, at the end of the string, that's some bad grammar there. All right, so at the end of the string, there is a 100-gram mass. String is vibrating in a standing wave showing 1.5 wavelengths. What's the period and so forth. All right. So this comes straight from the analysis, kind of the analysis that you would do with a string vibrator. Then over here, there's a pulley. So I have a string running, and just differentiate. I have a string running here, and then I have a 100-gram mass. It's vibrating so that there's 1.5 wavelengths. So this is a node here when done correctly, and this is a node here. And so 1.5 wavelengths, well, I know what a full wave looks like. Each one of these loops here is a half a wave, so I've got 1.5 of them, so, sorry, 1.5 waves, so I've got 3 of these loops. It's a third harmonic. So that's basically what it would look like. So the first question is, what is the period of the wave? Well, I say that it's vibrating at a frequency of 60 hertz. But let's use some different numbers just so that I'm not just giving you the answers. So let's make that 200 grams, and we'll make this 50 hertz. Hertz is the unit of frequency, so I know my frequency is 50 hertz. How do I find the period?
1/50.
Say it again?
1/50.
Yeah. So the period is 1 over the frequency, which would be 1 over 50 in this case, which is 0.02 seconds.
Okay, quick question.
Yes, ma'am.
You got the line right there. And you, did the little loops, the nodes and antinodes.
Right.
What prompted you to do that?
All right, when the line is just there, I haven't turned the machine on yet. As soon as you turn on the machine and the thing is vibrating up and down, that's when I'm gonna start getting nodes and antinodes.
Oh, okay. Duh.
So, and in the problem itself, it says that there's 1.5 wavelengths. Well, that's 1 wavelength plus a half, so 1.5.
Okay.
Is that sufficient?
Yeah.
Okay. Other questions up to here?
That 0.02, if we got a really big number for that, should we just round it to 2?
Oh, well, this one, I believe, comes out exact because I used
Yeah.
50, but with 60, 3 significant figures, is that?
Okay.
Just
Okay, if I did-
enough so that, don't round it off so much that I can't tell whether you know what you're doing or not.
Okay, is it okay if I went more?
Oh, yeah,
Okay.
okay. Or since it's gonna be repeated, I think, when you get to the repeated number, you can put a line over the repeated number. I know what you're doing. Other questions up to here? All right, so the next one was, what is the tension in the string? Well, this mass right here should be in equilibrium. And did I actually state that? I just said it was hanging. It is in equilibrium, so let's look at the forces. What are the 2 forces acting on that mass? Normal force from what? I heard weight and normal force.
Is it weight and tension?
Okay, I'll agree with tension. So someone like, if it's normal force involved here, it's gotta be touching something. So we'll go with Tana's suggestion of tension. How do you find weight? I heard mass times and then not what Stuart said after that. What did you say?
Gravity.
Acceleration.
Thank you. I assume you would have done it correctly on paper.
Yeah.
And so the mass, in order to get it into nice units, I gave it to you in grams, so let's put it into kilograms. So that's 0.2 kilograms. So that's 0.2 kilograms times 9.8 meters per second squared. And you end up with 1.96 newtons, I think.
And that would be for the tension in the string, or is that just, are we just finding the mass of the object? Or not the mass, the weight of the object?
Right here, we are just finding the weight of the object. However, if this is in equilibrium,
Then they're the same thing.
yeah, then the tension and the weight are equal in magnitude. Other questions to hear? All right, so that's the weight, or that's the tension. Wavelength of the wave. I give one other piece of information that the string vibrator is 1.2 meters from the pulley. In other words, the distance from here to here is 1.2 meters. Now I've got 3 loops here that are all the same size. They should be all the same size. So I can find out what, this is a slightly different method than what I did before. So I know that one of them, well, if I got 3 of these things in 1.2 meters, each of these has to be 0.4 meters. I should have picked a different number because this is basically giving you an answer. So therefore, a full wave, the wavelength would be 2 of those, or 0.8 meters. Or, I know I've got 1.5 waves in this 1.2 meters, so 1.2 meters is equal to 1.5 wavelengths. And so you can find, divide by 1.5. And you get the same answer.
Can you repeat that process one more time, please?
The first one or the second one?
The first one.
All right. So let me just use different numbers this time. Let's make this 2.1 meters. Because I know I've got 3 of these little loops here. If I'm at a harmonic, the size of these loops should be the same, despite the way that I've drawn it. That and that and that all should be the same. So I can easily find the size of one of them just by, well, I've got 3 of these things that go into that amount of distance. And for those who just woke up, this is different than what I had written down before I changed the number. So I just divide that by 3, and that tells me how long one of these is. So in this case, it would be 0.7 meters. But a full wave is 2 of these loops, and so the wavelength would be twice that.
Alright, I see.
So we're not counting that extra piece right there?
When I want the wavelength, all I want is that distance right there. Now the next question is, what is the speed of the wave? Oh, yes, Amina.
Is the 1.5 from this problem, because you put 1.5?
Yes, yeah, because it says in the problem, there's 1.5 waves. Yeah,
Okay.
1.5 wavelengths, so that's the 1.5 wavelengths. Is that good? All right. Other questions before I move on?
Yeah, I didn't understand what y'all were just talking about.
She was wondering where the 1.5 came from. The 1.5 comes from the problem where I say there's 1.5 wavelengths.
Yeah. So, if you gave us the wavelength, why are you asking for it?
No, I didn't give you the wavelength, I told you how many wavelengths there were, not the actual length itself.
Okay, gotcha.
Okay.
So should I have been had divided that by 3? I mean, yeah, dividing that by 3.
No, that would just tell you a half wave, that would tell you basically, I got 1.5 waves here, so that means I've got,
Gotcha.
you know, that's a half wave, that's a half wave, that's a half wave. So dividing 1.5 by 3 doesn't tell you much.
Okay.
Okay, so the next one is the speed of the wave. We have 2 formulas for the speed of a wave. we have only enough information right now to do one of them. But our two formulas for the speed of a wave along a string are frequency times wavelength, which is generic for any wave that you're dealing with, or the square root of the tension divided by the wavelength. Divided by the linear density. Well, we have frequency, we have wavelength, we have tension, we don't have speed, and we don't have linear density. So this is what we're trying to find here for parts D. Well, let's multiply the two things we do know. So in the way I have the problem right now, that's 50 hertz times our wavelength now 1.4 meters. Because I changed the length of the rope. Which is 70 units. Somebody just said it quietly. Yes. And now we know the speed, we can actually find linear density. And on the test where I've done this, that last question is generally the most missed one. I think there's a combination of factors there, but considering it's one part of one problem, it doesn't keep you from making A. But the problem for the last bit, given our numbers currently, I have 70 is my speed, is equal to the square root of my tension, 1.96 over the linear density. And that's the problem we're solving.